Hello, my name is Jennifer Padbeck, and I would like to welcome you to our HAMAMATSU Photonics webinar. I'm going to talk about the low light measurement, the fluorescence in the analytical field. Let's start by taking a closer look which topics we are going to discuss today. First off, I would like to give a brief overview of the HAMAMATSU as a company. Then we will have a closer look into the basic principle of fluorescence. I will continue with the requirement of how we can detect a fluorescent signal. As a bigger topic, we will look into some applications. I will also concentrate on suitable products from HAMAMATSU Photonics. Then I will finish with this webinar with a short summary and how to contact me or one of my colleagues if you might have open questions or you need more information on a product. Before we look deeper into the topics I'm going to discuss today, I would like to show you briefly what's new in the fluorescence world. A research group from the Indiana University South Bend developed a new biosensor which can detect glyphosate herbicide in soil and water samples. Glyphosate is widely used in the agriculture field, but has been also found to be a risk of developing non-Hodgkin lymphoma, a cancer of the immune system. Current methods have drawbacks that limit real-time detection and require often bulky equipment. On top, the need of testing frequently in large numbers is very challenging, expensive, and time-consuming. This newly developed biosensor is based on a protein from bacteria that has been re-engineered to bind to glyphosate. The sensor then produces a fluorescent light signal that can be detected and used to quantify how much glyphosate is in a sample. This short excursion shows how broad the world of fluorescence and its application can be. But now I would like to have a look onto our topics of today. Let's start with a brief overview of HAMAMATSU Photonics. It has been established in 1953 and is located in Hamamatsu, which is approximately 300 kilometers south of Tokyo. In total, HAMAMATSU Photonics has 10 department bases. 3 of them are only devoted to research and the development of new technologies. To keep being a pioneer in new technologies, HAMAMATSU spends over 9% on R&D departments. With over 5,000 employees working all over the world, HAMAMATSU Photonics is a steady growing international company. But especially proud makes us that some products have contributed to 3 Nobel Prizes. 2 Nobel Prizes have been awarded at the Kamikani, respectively Super Kamikani experiment, for the observation of neutrinos and neutrino oscillation. Our 20-inch PMT, which is the world's largest, could capture this phenomenon. 1 Nobel Prize was awarded in 2013 for the discovery of the Higgs boson at the Large Hadron Collider, which is one of 7 stationary experiments at CERN. Our silicon strip detectors are implemented in these detector systems. And as a last point, HAMAMATSU Photonics has over 15,000 products in the standard portfolio. In the following slide, I would like to give you a short overview. HAMAMATSU offers different kinds of light and radiation sources, for example LEDs, lamps, and lamps modules, which include the electronics. But we also offer optical components, like fiber optic plates, flow cells, and SIR substrates, which stands for Surface Enhanced Raman Spectroscopy. The portfolio also includes lasers, like continuous wavelength lasers, but also pulsed laser diodes. Complete systems are also part of our portfolio. But the biggest portfolio can be found in optical sensors, which include, for example, photodiodes ranging from the UV to the far ER range, PMTs, image sensors, spectrometers, infrared detectors, and X-ray sensors, just to name some of the typical sensors. But we also offer complete systems, for example, the drug screening system or the pinhole inspection unit. We will come back to some of the mentioned products later during the application section of this webinar. But first, let us start with the basic principle of the phenomenon of fluorescence. Fluorescence is the emission of light by a substance that has absorbed light or other electromagnetic radiation. In most cases, the emitted light has a longer wavelength and therefore lower energy than the absorbed radiation. If we have a look at the Jablonski diagram, we can see a typical picture of fluorescence. A photon of higher energy is absorbed and excites an electron from the ground state to the excitation state. The system relaxes then vibrationally and fluorescence at a longer wavelength. Fluorescence is therefore photoluminescence as a result of singlet-singlet electronic relaxation. This has a typical lifetime of nanoseconds. It is also possible that the electron crosses in the intersystem and relaxes then from the triplet state. In this case, we speak of phosphorescence, which is a result of triplet-singlet electronic relaxation. Here we have a typical lifetime of microseconds to even hours. If we look at chlorophyll as an example, we can see a part of the flower under white illumination. If we illuminate the flower with UV light, we can observe red fluorescence of the chlorophyll. In any case, as mentioned before, fluorescence is a weak light phenomenon and lasts typically only for nanoseconds. This brings us to the requirements of a detector in order to detect fluorescence. As we said before, a fluorescent signal is a weak light phenomenon and lasts typically only nanoseconds, but can lie between picoseconds to microseconds. Therefore, we have the following requirements for our detector. It has to have a high sensitivity, even photocounting could be necessary. It should have low dark counts to minimize dark current and background. We need wide dynamic range, and of course, we need fast detectors, otherwise we don't have the possibility to detect a fluorescent signal. If we have a closer look at 3 of Hamamatsu's detector systems, we see that these can fulfill the requirements. APDs are photodiodes with internal gain produced by the application of a reverse voltage. They have a higher signal-to-noise ratio than PIN photodiodes, as well as fast time response, low dark current, and high sensitivity. Our multi-pixel photon counters, short for MPPC, also known as silicon photomultipliers, is a solid-state photomultiplier made out of high-density matrix of Geiger mode operating avalanche photodiodes, which are also known as SPAD. These stand for single photon avalanche photodiode. These SPADs have high internal gain, which enables single photon detection. MPPCs have low dark counts, high photon detection efficiency, and are very robust and are immune to any magnetic fields. All of these features make them well suited for ultra-low light applications. Our photomultipliers exceed in all these categories, but make them also the most expensive of these 3. PMT are specially suited for single photon counting. After we saw how a fluorescent signal is created and what requirements our detector has to meet, we have a closer look now into the fluorescence applications. We will shortly outline 5 of those fluorescent techniques, and which detector types are interesting for those. Starting with fluorescence lifetime imaging, short for FLIM. The basic goal of FLIM is to create an image of a sample with functional information. That include many types of information, and all of those can be reconstructed via the fluorescence lifetime of either autofluorescent samples or fluorophores. Fluorescence lifetime can be dependent of, for example, on the pH environment, the temperature of the sample, or for example, on whether there are binding partners, which can act as an energy acceptor. All of those parameters can have an effect on the lifetime, whereas other critical parameters in laser microscopy do not influence the lifetime. Thereby, FLIM is independent on the fluorophore concentration, photobleaching, and also on the absorption within the sample, hence on the irradiated laser intensity. In order to obtain reliable lifetime information with high data quality, FLIM needs sophisticated detection technology. The fluorescent signals are generally fast and weak. This means that a suitable detector must combine 3 critical specifications: high speed, low timing jitter, or high temporal stability, and the ability to detect single photons. For this, we offer several technology concepts. Quantarus is a fully integrated turnkey system ready to use at the user side. On component basis, we recommend either our multi-pixel photon counters or we recommend the usage of our photomultiplier tubes. As a high-end option with best temporal specifications, our hybrid photodetectors can be used. They combine the technology of the PMT with a semiconductor amplifier. We are also continuously improving and broadening our lineup of suitable FLIM detectors. The first PMT is our new NIR PMT. It combines a cathode with sensitivity up to 1400 nanometers with a very small form factor. The second is our new NIR PMT up to 900 nanometers with extended thermoelectric cooling. By this, signal-to-noise ratio is improved in comparison to previous types. And the last is a dual-mode PMT module, which combines analog detection with a photon counting circuit. This means there is extended dynamic range for very small and rather large signals. As another fluorescence application, we have a look at flow cytometry, which is a measurement of cell characteristics, as the cell size or type, or the number of cells. In this process, a sample containing cells is suspended in a fluid and injected into the flow cytometer. The sample is focused to ideally flow one cell at a time through a laser, where the scattered light is characteristic to the cells and their nature. Cells can additionally be labeled with fluorescence markers, so light is absorbed and then emitted in a band of wavelength. Scattered and fluorescence light can then be detected, and various information can be visualized in scatter plots as shown on the right. In this scatter plot, different cell types are shown in these clusters, like the monocytes. Coming now to suitable products for flow cytometry instruments, HAMAMATSU Photonics can offer a broad variety from optical components to optical sensors. Starting with flow cells, which we have a standard portfolio, but we also offer the possibility to customize. New on the market are also anti-reflection coated flow cells, which minimize stray light on the surface. As mentioned before, we also offer a broad band of avalanche photodiodes, which are low-cost solutions but also offer high sensitivity and speed. Coming to our PMT portfolio, I would like to mention at this point that also there we have a broad band of different kinds, like different photocathodes, window materials, or head-on or side-on PMTs. The last product I would like to introduce is our PMT module, which is designed to function as a 6-channel spectrum detector. Compared to the conventional type, this PMT supports optical fibers with large core diameter up to 1000 micrometers. This brings us to the second fluorescence application in the medical field. Polymerase chain reaction, short PCR, is a technique to make million copies of a specific DNA. This method is, at the moment, of high interest, as the PCR technique is key for virus detection. Here we can see a schematic drawing of one cycle of a PCR process. First, the sample is heated, so the original DNA denatures and separates into single-stranded DNAs. Using single nucleotides and primers as starting points, 2 new strands of DNA form using the original strands as tablet. Next step is called hybridization and describes the attachment of the primers to the DNA. The new strands are then used to create each 2 new copies. This amplification is repeated 30 to 40 times. To detect a specific bacteria or virus, a fluorescence dye or marker is added. These markers are multiplied as well and can be detected afterwards. Again, the detection of these fluorescent markers are low-light measurements, and the best-suited detectors bring us to PMTs and multi-pixel photon counters. But also, compact camera systems are suitable, like our CMOS camera. This camera has high sensitivity, high signal-to-noise ratio, ultra-low readout noise, and those are just to name a few. As the last application, we have a deeper look into a special technique of microscopy, the two-photon microscopy. For questions that require imaging live cells for extended time periods deep within tissues, two-photon microscopy is the current method of choice. As we see in the drawing, two-photon microscopy also, like confocal microscopy, uses a laser to excite a fluorescent tag within a sample. Detectors then measure the emitted light. Unlike the lasers used for confocal microscopy, which provide single-photon excitation, the lasers used in two-photon microscopy excite by using near-simultaneous absorption of 2 long wavelength photons, usually in the range of 800 nanometers. This leads to several distinct benefits. The long wavelengths used for two-photon microscopy are less damaging and penetrate more deeply into the tissues. In addition, the requirement for near simultaneous absorption of two photons means that excitation is only achieved near the focal plane, where the laser light is most centered. This has two distinct advantages. First is that there is little tissue damage to the regions above and below the confocal plane. The second is that there is no out-of-focus light that could make the image blurry and difficult to interpret. As we are also continuously broadening our PMT portfolio, which are suitable for two-photon microscopy, I want you to show these 3 new PMT modules. At first, we can find a new version of a high-running PMT. This high quantum efficiency PMT comes with higher maximum anode current of 40 microamperes, which can act as a protection of the photocathode, and the dynamic range is significantly improved. The new version also comes with 2 different outputs. As a second product, I would like to show the new large effective area PMT. This PMT module employs a gas photocathode for high sensitivity in the vis region. The area is 14 × 14 square millimeters and has a built-on amplifier which delivers low noise and high speed. The photosensor on the right is also using a gas photocathode, which includes a gate function of 1 millisecond 2dC. This is ideal for microscopic applications which uses a laser as excitation. The gate function can protect the PMT module electronically from excessive light, such as fluctuation background light. As my last application, we will have a look at HPLC, high-performance liquid chromatography, or commonly known as HPLC, is an analytical technique used to separate, identify, or quantify each component in a mixture. The mixture is separated using the basic principle of column chromatography and then identified and quantified by spectroscopy. HPLC is thus basically a highly improved form of column liquid chromatography. Instead of a solvent being allowed to drip through a column under gravity, it is forced through under high pressures of up to 400 atmospheres. The purification takes place in a separation column between a stationary and a mobile phase. The stationary phase is a granule material with very small porous particles in a separation column. The mobile phase, on the other hand, is a solvent which is forced at high pressures through the separation column. The sample is then injected into the mobile phase using a syringe. The individual components of the sample migrate through the column at different rates because they are retained to a varying degree by interactions with the stationary phase. After leaving the column, the individual substances are detected by a suitable detector and passed on as a signal to the HPLC software on the computer. At the end of this operation, a chromatogram is obtained, which allows the identification and quantification of different substances. Depending on the information one wishes to observe, there are different suitable HPLC detectors, as chemiluminescence, mass spectrometer, photodiode array, variable wavelength detector, or fluorescence detector. As this webinar concentrates on the fluorescence phenomenon, I would like to present 2 of HAMAMATSU products which are suitable for this application. First, I would like to show one of our high-performance PMTs, which has a wide response range from 185 to 900 nanometers. Dependent on the dimensioning of the end product, one can choose between head-on or side-on PMT. As a second suitable product, I would like to introduce our xenon and mercury xenon lamps. These lamps are filled with xenon or mercury xenon gas and emit white light at a high collect temperature of 6000 kelvins. With a continuous spectrum from the UV to the visible to the infrared range, these lamps are best suited for HPLC application. Mercury xenon lamps produce high radiant energy, especially in the UV region, due to the optimum mixture of the mercury and xenon gas. Our lamps, depending on the version, have a guaranteed lifetime of over 3000 hours. And with this, I'm almost at the end of my webinar. Let's have a short look at the summary. Today we saw that fluorescence detection is found in various applications, and we looked a bit deeper into 5. First, fluorescence lifetime imaging, or FLIM, flow cytometry, PCR detection, two-photon microscopy, and HPLC. We also saw that fluorescent signals are weak and very fast, typically nanoseconds. HAMAMATSU can offer all kinds of suitable detectors and light sources. If you haven't found the right detector in this presentation or on our website, please feel free to contact us anytime and ask for customization. If there are open questions or you would like to know more about one of our products, please either contact me directly or one of my colleagues. Thank you very much for your attention.